There's a lot of interest recently in how to make search more efficient, mostly how to make it parallel, how to do indexing faster, how to access data faster, how to search big data. And the topic today is different. Topic today is see how we can take advantage of linguistic information at the level of words, at the level of sentences, and at the level of paragraphs. Because in my opinion, like myself as a search engineer, I'm pretty happy today with the efficiency, how fast the whole thing works. I know that providing search result to 200 million customers, like population of this country which is searching. So overall, I'm pretty confident whatever algorithm I develop, they're going to work fast, and they're going to scale, and I don't have to worry about it myself, which is most important. So the purpose of this work is to do the same thing for relevance. Let's engineers, let's people, open source contributor in search system, in Solr, in Elasticsearch. They're mostly obsessed with efficiency, with parallelness, and let them use linguistic tools so they don't have to get deep into linguistics, but see if for them it works. So what we're going to do? What kind of linguistic information is beneficial? So what can we take advantage of? Advanced state-of-art machine learning of linguistic data specifically for search. Have a let's say black box open source component for search engineers so they can plug it in, run complex queries, or be happy or not happy. So, but at least they don't have to spend time learning linguistics and getting into details. So this is the goal. And then from the computer science part, this is an interesting problem in terms of graph representation, because to represent the structure of paragraphs, we need non-trivial graph, and it's basically interesting object to play with. And I'll also repeat these links later. This project is a contribution to Apache OpenNLP project, and the code is available there. And also there is a version on Google Code. Let's first talk about the problems. We're starting with Google. The question is, which specialist doctor should treat my tuberculosis? I don't know the specialty name. And so if you know what you're searching about, probably not going to experience this. And what you see, what you're looking for the specialist's name. You're looking for it, but you don't mention it in your search result because you don't know it. And then what Google gives you, Google finds in search results and keywords, they are somewhat relevant, but Google could have been much better if they, while indexing, they somehow connect doctor and tuberculosis. Let's see how it can be done. And this is an example of an offer. We are building a search engine. There are two portions of text for indexing. In lung disease, it is cured by doctor. So here we have the link between tuberculosis, disease, and cured by doctor. So we have two different sentences, but there's an after. It relates to disease. Therefore, we can link the sentence. So naive approach, what typical search engine like Solr, Elasticsearch, and I suspect Google and Bing do, they usually ignore boundary between sentences. If you just ignore boundary between sentences, sometimes you cannot just assume that the topic is the same, because the next sentence can talk about something totally different. So what we're going to do, we're going to see how we take advantage. We're going to verify different links between sentences. We see how sentences are interconnected, and then index accordingly. So in this case, at indexing time, we put a phrase, tuberculosis, disease, doctors, and if we did it at indexing time, we would do better answering this question. Okay? And this is one linguistic phenomena, coreferences, anaphora. So we have two sentences, and they are linked by pronoun. And the purpose of this work basically explore what kind of linguistic theories, how can we exceed the boundary of a sentence and answer more complicated questions. Another question, like I specifically put this question as a natural language and kind of expressing why do I have to pay Obamacare tax for not having health insurance if I stay abroad? See, this is a single sentence, but these are basically two situations, two main phrases. Obama, like Affordable Care Act, and Google does a good job at having synonym, but not really combining two phrases. So answers basically it's hard from the snippet, hard from the snippets to understand if answer is correct or not. So one of the things we do in this work, we have this question, we have this snippet, and see for longer question, Google and Bing gives longer snippet. So what can we do? And this is one evaluation in this study. We can take first 100, 50, 100 or 1,000 search results and actually compare. Once we have linguistic technology, our comparison not going to be by keyword, but by structured information, which we will see. So then maybe there is a much better answer number 100. So what we do, we take each search result, each answer, and then compare with question. We don't want to maintain index similar to what Google does. What we want to apply linguistic information. So we get Google results and research them. We can do it with Google because there's no API, but you can do it with Bing and Yahoo. And this is a part of evaluation. So we can apply linguistic technology and rank based on similarity. And I'm going to talk more about how the similarity works.
Why did you say you can't do Google, but you can?
Okay, so Google does not provide search engine API, and Bing and Yahoo and other companies do. So we can get search results. We don't have to worry about index. Then we can re-rank them and improve, hopefully improve relevance. So motivations, applications in search, the operation on Parse Thicket, which I'm going to show called syntactic generalization. We talk about first sentences, then paragraphs, then some case study, then consider more linguistic theories for discourse, how text is organized, then briefly evaluation, and back to open source contribution. So basically the goal of this presentation is become familiar with this graph, and I'm going to briefly kind of outline here the plan. So these are parse trees. And we're going to give examples, so if you're not familiar, at least by example, you'll see how they work and how they help with relevance. So these are short sentences, phrases. These are multiple trees for paragraphs. And by finding similarity, we overcome the problem of dealing with keywords. So this is not for you to understand right now what it is about. This is the end goal of this presentation, to be fluent basically in these graphs, which you call Parse Thicket. Again, you can see, so the typical approach to search, to clustering, to text analysis, just take each word from here, combine them together, calculate statistics, and then see how frequent this keyword here, how frequent this keyword there. So basically, keyword approach compared to this approach, you just ignore all the links. But you see, there's a lot of different links. And if you just throw away this information without understanding how we do it, you can feel how poor our analysis is going to be. So I'll repeat, typical search, Lucene-based search, solid search, elastic search is basically taking only keywords and counting them, how frequently they are in documents, how frequently they are in how frequent is this term in the call corpus, how frequent it is in documents, maybe how close these keywords in text, compared with all this richness of information. So we're going to explore what it is and how to take advantage of it. I'll start with eBay search. I'll start with simple phrases. When you search hydroponic filter with carbon, it is important to analyze phrase structure. That it's something with modifiers with something. So you cannot just say that something hydroponic, air, filter, carbon. You have to maintain the structure when you combine questions, when you find relevant products for questions. So for product search, it is essential to maintain phrase structure. Another example, this is example of our project where this technology was applied. This is not a typical search, it's more like recommendations based on your posting. The query is Lady Gaga, performance name, who wants her big store. That was project at StubHub, which is a part of eBay. Just an example where we have complicated queries. Another search engine, Yandex. Pay tax on income abroad. If you just do keywords, it's citizens living abroad. So basically, if you don't maintain structure, you do not understand. So idea of this approach based on parse trees, we're never going to really understand human language. However, since parsing is domain independent, let's take everything we can, take advantage of everything we can from parsing, from something we can do in domain independent manner. For example, we only build search engine for tax calculation. Then we know what is citizen, how to pay tax, what kind of income. Then we use taxonomy, then we're in a little bit better shape. In this approach, it's a pure syntactic information because anything can be parsed. A rhetoric structure can be determined without really knowing what domain is, and then see how far we can go just using this domain-independent approach. So if we do quotes, we improve a little bit. So basically, understanding, like doing phrase matching, it's more search engine for you insert quotes. Okay? So the better we maintain, yes?
How does this compare, for example, Google suggests things as you type, as you not.
Okay, autocomplete feature. For autocomplete feature, that's n-grams.
To kind of lead you towards some kind of a structure, right? So this
Okay, so basically it's a pre-recorded tree based on a priori. In advance, they know what are the typical n-grams, and once you start first or second keyword, as you type, it reduces the possibilities.
So
it's not a phrase structure, it's n-gram analysis. It's still the keyword.
Structure analysis, and then they just present you the n-grams, no?
Okay, so you have accumulate all frequent phrases, what people search. Then you start typing your first word. The more letters you type, the smaller the number of possible combinations. And it's independent of answers, right? Independent of search results, because they already know typical queries. And basically, as you type each next character, they will keep reducing the set of possibilities. This is not about comparing possible search results, because for autocomplete, you don't need search results.
So you're saying that's at the sentence level, is not at the group of sentences, right?
It's n-gram. First, theoretically,
That's correct.
yeah, theoretically, you can do cross-boundary between sentences, but really, you cannot go too far. So for autocomplete, they use it usually short, and you don't need this technology. This is for longer questions.
It's like entity relationship where there's an intervening block of stuff that might be relevant.
I mean, this approach?
No, I'm saying, yeah, your approach is for an entity relationship when there might be an intervening block.
Okay, so we have multiple entities, we have multiple attributes, and you don't know for sure which relates to which, so you have to build parse tree, which, so basically if the question, how can I get short focus zoom lens for digital camera? This is parse tree, predicate. This is a tree, you have links between the words, nodes are labeled with words, we have relations, And then you have a potential answer. So typical search in this setting is just what are the common keywords? Just compute common keywords, taking into account frequency, if you have enough data. And if you don't, you cannot take into account frequency. This approach, keywords do not live on their own. They only live as a part of tree. So compare trees. If what is shown here is the maximal common subtree. Okay, so this is important step with equations here.
Yes, so what kind of parser are you using? Grammar? It's a CCG, tag, HD,
Okay.
whatever?
So this is what we call dependency grammar. There are different approaches. This component uses Stanford NLP and OpenNLP. And this project is contribution to OpenNLP. So most of the time, the parsing is from OpenNLP, which is statistical. This particular picture, just for demonstration, is a different kind of parsing, but it doesn't matter. I mean, you can have different way of constructing trees, as long as you construct the same way, tree for question and tree for answer, you match them, you find maximal common subgraph, and the answer which has the highest, the largest common subgraph supposed to be the best.
But that depends on how deep it is, right? Because you cannot parse the subgraphs until you start with the top, so you can need to iterate many times, right?
Okay, so now we're discussing how we find common subgraphs. One of the algorithms, and in this project we do both, we actually do navigate graphs using a JGraphT library, or we do it by phrases. By phrases means we find paths in these graphs, and then we try to align them. I'll show examples. So this is a comparison. So for search engineers, that's where search engineering starts, Solar, and domain is from entertainment. The question is Lady Gaga sings. If we have just a keyword search, we have an index for default search engine, default request handler in Solar. It doesn't care about the order of words, doesn't care about phrases. So Lady Gaga does a belly dance, and dance is misspelled. Now we consider exactly the same index, but instead of using term frequency inverse document frequency, we re-rank these results by parsers, which are simple in this case. And now, since the first, for the same question, the first answer is Lady Gaga sings pop. So the simplest possible examples. Your search index is just 10 very simple documents. Each document is not even a sentence, like 10 keywords. And even with 3 keywords, this system demonstrates that default search in Solr can be outperformed. And this is a standard for like startup search engine, Elasticsearch in Solr. So the idea is, as you see, a little bit for those who use Solr, here, if you see the request, it's a local index, and this request handler called syntactic generalization. So the idea, you have your Solr running, you don't have to understand how it works, how you basically just indicate different Java class in how you run your search. You install linguistics model, basically model file, which you have to download, and then you, basically that's how all you have to do to improve the relevance. And the rest of Solr features are not touched. It's still distributed, it still can have huge index, still the same big data. So by using the same data set, by re-ranking your search results, by comparing parse trees, even as simple example as this, you can improve relevance.
But isn't that ranking dependent on the content? So how can you provide them with a...
Okay. For example, if your ranking is depending, like you do, if you rank by popularity, by price, by location, then this is not approachable. It's only about relevance. However, if you can combine relevance score with popularity score, and I would say the formula is you multiply, I would say default, what you should, in my opinion, try. Multiply popularity by relevance. So in your score. So you do this linguistic score. You have your location-based score, or whatever price score or product popularity score. If you always show very popular products, your customers are not happy because they don't find what they want. If you always show only relevant products, you may don't have, your income, your click-through rate might not be enough. So let's make a simple model. Let's multiply popularity by relevance. Relevance is achieved by linguistic technology. Popularity or location by other means. Okay? Yeah.
Why is Google not doing this? Why are they not providing the API?
Okay. So Google does not provide API for Google search result for some business reason. And Google, I think, doesn't do linguistic analysis.
Actually, they are doing.
Okay, so possibly, okay, I don't know. So they don't publish, right? Possibly they do, I think. So this is example. Now we have, so how we do simplified way to match parse trees? You have the word, you have part of speech. So when you matching, if you're matching, if it is the same word, usually the same part of speech, so you have the same word and part of speech. If words are different, but part of speech is the same, like adjective, you can still match, and then instead of word, you get star. So whatever doesn't match component, you get star. Whatever matches, you have either part of speech or word. So for two, this is a way using by phrase level, two verb phrases, use the digital camera zoom and get short focus. We find maximal common subpath or subphrase. So this is the expression which works. And we can even interpret it. So verb, any kind of verb, any kind of feature, do something with some kind of zoom, something for something else. This is just for us to represent it. Then the higher the number of words with parts of speech, then the higher the score. So it still comes down to the score, just that score now is not based on frequency, but based on the size of common parse tree. In this case, common subphrase.
Wouldn't this be destroyed by things like the difference between active and passive voice?
Okay,
or
very good question. I didn't mention that, but trees needs to be normalized. For example, camera with digital zoom should be normalized to digital zoom camera. And we apply transformation like normalization of part trees. So you first normalize and then match. Because otherwise, like you match noun phrases, you have to convert passive voice always with active voice to match. That's exactly what we have to do.
Genitive and preposition of and things like.
So basically, yeah, you have to remove and then normalize. So for matching, you need to normalize. Similarly, more sentences, similar, and then the phrase, another example. Okay, now Parse Thicket. So we are done with individual sentences, and possibly Google has that. Let's see if, how we can do better, and what kind of linguistics works in between sentences. We want to represent linguistic structure of paragraph of text, combining parse trees, individual parse trees. So we have parse trees and then some links, in additional links between words, which are not syntactic. And the way it is used for search, we have a question. We build the Parse Thicket for question. Usually it's a question at the size of paragraph. For example, recommendation or some, we want to find documents similar to a particular portion of text or a web page. Then we build Parse Thicket for answers, and then we generalize. Basically match them according to what I showed. And we're going to consider examples. Let's consider a big example and then go step by step. So these are two portions of text. One way is consider this is a question, or this is a topic, and we want to find documents on the web for this topic. So using Bing API, we extract keywords, search for different documents, and then for candidate assess similarity. Or we do clustering, using this approach to compute similarity between sentences. We're going to start with keywords, then proceed to the level of sentences, and then all the way to the paragraphs, and see how much information we have. So going to be baseline is middle forward. Pairwise sentence matching, we're going to take each sentence from first text. I'm going to go back. We take each sentence from first and then compare each sentence from the second. Because usually information is distributed between sentences, right? What we want to do, we want to compute similarity irrespective of how information is distributed. Maybe it's one sentence here and 10 sentences here. As long as it's the same information, they should be similar. So we need to apply ways, phrases, and meaning to distribute through sentences, which we're going to do using discourse structure. So we have keywords. That's a typical search approach. We have keywords, possibly with frequencies. Then we have pairwise. Again, we take each pairs of sentence, each with each, right? Because we don't know in advance. We cannot align sentences. We try to compare each with each, how similar they are. And if it's nothing, then we just don't include it in the text. So these are the phrases which are common between those portions of text. By the way, is notation clear by now? We have words and parts of speech. If words are different, but parts of speech are the same, then we have a star. So for example, here, the evidence is in both texts. Then something, okay? Now it's much richer. Now, instead, we take into account additional meanings. For that, we're going to use richer information about the text. For example, communicative action. This is politics. Agents express their opinions. They agree or disagree. And by knowing that we have the way to express opinion, like suggest, and we have the topic, like war, Iran, nuclear weapon, we get more structure. And if we have more structure, we can extract similarity, rich information about similarity. So if we go back to this text, and the problem is clustering or search, if we use keywords, think of it, we have like 10-dimensional thing. How many keywords? 15-dimensional things. But the deeper we go into the structure of language, the richer feature set we're going to use. And not in this approach, we do matching of parse trees. But we don't have to do, we can still do traditional machine learning like SVM. Once we get a richer set of features, we can apply traditional statistical learning and still do better. Okay? This approach here called kernel based. Instead of dealing with parse trees, we encode each subtree as a feature, consider each subtree as a feature, and then it's a multidimensional SVM. And that is a competitive approach. Now let's have a little bit funny example of how this technology is used. Agent acting on behalf of a user posting messages to maintain friendship. So here's the problem. On average, people have 200-300 friends on Facebook. I'm a little bit switching from technology now to like application area just to have some rest from formal stuff. So if I don't want to lose my friends. If I keep sitting and spending time on Facebook, I have to spend a few hours per week just talking to my friends. But then I'm not real friends. Most of them are my colleagues, people I met. I want to maintain the friendship, but I don't want to spend time. So why doesn't an agent do it for me? For my distant friend, he got a new dog, something happened, new travel, new something. I don't really care. But I might need him in a couple of years. So what this agent does, it takes the posting, goes on the web, finds something relevant, and posts for me. But the catch is it has to be relevant. And for relevancy, you need this technology. So my friend, I worked some time ago, maybe 8 years ago. I don't care about him, and he's enjoying sunset over Lake Tahoe. So the system takes his posting, possibly some expressions from other friends, which possibly care about him. Then I go to Bing API, then from the trace, I search for different text. Some blog, somebody actually went to Lake Tahoe and wrote something. So this is the posting. And he probably remembers me because I care what he does, although I don't. So the idea of this technology is basically, if you can be relevant, you can post messages on behalf of human, and you can scale it up and really maintain 2, 3, 500 friends. Yes?
That's called a chapter call.
Okay, particular application. Not really charted. There's not really a notion of dialogue here, just for simplicity. It's more, if I can find relevant information about anything, then for every of my friends I can find something. So he would remember. And it doesn't matter if it's true or false, the quality of information exchange on Facebook is not that high. So let's just play.
But can we stateless like that? Because if you respond, maybe if you respond something with context, so you have to maintain now the whole context of the conversation.
Actually, if he responds, okay, so there's one attempt here to reason about. There's one attempt here to reason about mental states, but this is a different technology. I'm not going to talk about it. I would say an example. Obviously, I tried this with my friends. So my friends posted a picture about dancing tango, and my agent just got some capture and basically found information. It's pretty much tango and wedding. So they got upset. His girlfriend got upset, and this is an actual human conversation between them and me, saying, basically, I can foresee some worrying situations. So people are not always happy about it. They were probably upset that I mentioned wedding. I don't know what kind of relationship we were, but nevertheless, 5 months later, they did get married. We're going back to the boring stuff. Now we're going deeper into linguistics. What are the sources? So it says parse trees, links between words. If it's about anaphora, pronouns, same entity. If two sentences about the same thing, then it should be connected. A rhetoric structure, which we're going to consider briefly, and speech here. Now let's learn more how this works. So again, in blue, these are parse trees. In the red, so parse trees in blue stuff is like standard stuff to represent sentences. Red stuff is what we add. Here we add anaphora. Iran envoy says its nuclear development. See, if Iran says, the normal search would index Iran, envoy says its nuclear development. But we cannot just follow the order first. Because if it means we should index Iran envoy, Iran nuclear development. See, based on anaphoras, we should build our index and repeat the terms. Now, rhetoric structure evidence. So rhetoric structure include relationships between how portions of text is formatted. It's on a higher level than level of phrases and words. In this case, nuclear development is for peaceful purposes, but it has been fabricated by the USA. So we have the relationship. We have two portions of either one sentence or different sentence, which are related by different kind of relationship which are above text. So again, this is anaphora. This is a relationship of evidence. This is example of the same entity, Iran and Iran. Another same entity. Then communicative action, dispute. So basically, when we index text, we should not treat communicative actions as regular keywords, because nobody's, it's unlikely that people ask who will dispute over. The communicative action can be different. It's totally independent of the content. The subject is work on nuclear a weapon. It can be disputed, agreed, disagreed, explained. So it's totally independent. So when we build the index, we also have to take this into account. And when we build this Parse Thicket, if we have in two portions, we have the same relationship, we match it. It's going to be part of the future common subgraph. If relationships are different, we cannot match them. But what you see here, if we just match individual sentences, we take portion of here, and we can only use blue links. Now, using red links, we can actually switch. So the number of candidate phrases we can match is much higher. We can start on the top, then navigate here and continue here, right? So all possible expressions which can be matched, the number of these expressions is now much higher. Okay?
It is not clear. So what you're doing, you're analyzing one phrase with multiple algorithms or different phrases? With
Oh, no, not multiple algorithms. So if we have two sentences, and then there's a link, if you have two sentences, and link between two sentences, think of it as for search engine, we have 4 sentences. We start from the first, switch to the second, continue the second. We start with the second question, then jump back and continue. So if sentences are connected, remember my first example with tuberculosis, then you can cover multiple combinations. Maybe beginning of first sentence, but then end of second sentence.
And among other things, that disambiguous pronouns, kind of like the figures out who
So
the it refers to and things like that.
You don't know what's going to be asked. So, and you don't build index just randomly according to how sequence words occur in text. So instead, you take into account the laws that phrases are not random. There's no random sequence of phrases in text. There's a certain discourse structure they follow. So when you index, think of it, for search engineering, think of it as indexing. Directly interpreting this technology, basically instead of comparing parts of parse tree, you're comparing this whole structure. Okay. Let us zoom in and see more example. So just have it bigger. Iran review. So there are multiple agents. They are interacting. And the communicative actions are refusal, acceptance, proposing, and then condemning and disputing. So the way agents, the communication mode is independent of the subject. They dispute over work on something, but proposal to do something, but it can be other way around. So we compare communicative actions independently of the subject. Yes.
Okay, so apologies for being slow. I'm still trying to understand what is the diagram saying. You're trying to compare the equivalence or similarity of 2 or more sentences in a structurally independent way. Is that right?
Okay. So so far this is one paragraph. Remember, we're going to go back to this big graph when we're comparing 2. Now we have still one paragraph, not 2. So we're not assessing similarity yet. So far we're just building the Parse Thicket.
Okay, so we're building a Parse Thicket for one paragraph.
For one paragraph, yeah.
We're not comparing sentences between.
We're going to get there. We will compare.
Okay.
Let's go directly there. Since you're asking for the understanding, let's go there directly. Here. What I showed, we were drilled in. This is one paragraph. This is another paragraph. And then we try to find commonality. Remember, if we just find common keyword, just small links. If we ignore all red links and just do blue stuff, we still get some intersection, but much poorer. Okay.
Are you trying to say we build the thicket first, then try to find the commonality? Or
Of
find
course.
the commonality as we build it, or what?
Okay, we first build this graph, and then we find the similarity between as maximal common subgraphs.
Okay, and the commonality is a bunch of structural transforms.
Commonality is subgraph, but for search, it's size basically. So your search score is its size. For example, this is question. You have 10 answers. You build this for each, and the higher the number of nodes in green areas is overlap. The higher the number of nodes in green area, the higher the search result is supposed to be. And I repeat, if you ignore all red stuff, you still get the overlap. but it's much poorer, right? Basically, when you ignore red links, it means I don't care how people organize the structure. I just take into account phrases and how they occur in sentences. Maybe so the naive approach is just take keywords. I ignore all links. Next step, I do parse trees. I care how the sentences are organized, but I just assume people people communicate in random sentences. But this is not true, right? There's certain. So I first introduce object, then I introduce feature number 1, then I introduce feature number 2, and then I introduce a link, right? So if you take into account red links, it's much richer and much more expressive way to express similarity.
Is this related to topic models?
No. For topic models, it's still a keyword approach, but keyword is associated with feature spaces. It can work as a complementary, but the underlying idea is different.
So the red links are the set of structural relationships you showed earlier, right? And
Yeah.
could you bring us back to that slide, please? It's not obvious how you get from there.
Okay, so basically this, what I was showing is just this one.
Okay, can you
And-
show
okay,
the slide?
let's go back.
Structural transfer.
Yeah, let's go back. Let's go to the bigger, right? This one.
No, the slide that explicitly lists interrelationship.
Interrelation.
That-
Here.
There, yes.
Okay. So anaphora is propositions. Say meant to remember Iran. A rhetoric structure is like something elaborates on something. Elaboration means, for example, there's a different rhetoric structure relationship like causal link, temporal link, spatial link, just a sequence. So whatever, it's just that we need to match the same relationship in one text with the same relationship with another text. Okay, so rhetoric structure is clear.
What is anaphora?
Okay, anaphora is Boris said something. He was wrong. So Boris was wrong. So using a pronoun to refer to the name. Okay. So obviously, if, like, I'll repeat this example. Boris said something, he was wrong. If you ask, if Boris was wrong with your question, you have to match two sentences. But is it okay for your keywords? Is it okay to occur in different sentences? Sometimes it is acceptable. Sometimes it is not acceptable. So we need this notion of anaphora to understand if your keywords can be found in different sentences or not. And if you ignore it, basically you will get irrelevant results. I'm going to briefly, this is an example, just different visualization. Maybe for open source tools, this is Stanford OpenLP available. And if you want to go deeper into linguistics, if you don't want just to plug to your search in file, this is the same visualization. Stanford NLP gives you, this is a different way to represent trees, just as an example. And this is another open source, so you can get it and you can plug to your application. Red links between sentences. In my middle to detail, so there are text. And we need to read and classify. There are two classes of text. The keywords are the same. So if you just consider keywords, it's very hard to distinguish between classes. But it turns out that there are two different areas. Tax liability landlord renting office to a business. Tax liability of business owner renting an office from landlord. The same keyword but different order and a totally different topic. They cannot be matched. And if you use one as a question, you cannot do something as an answer from different class, right? Because it's going to be relevant. If you ignore, I would think if I talk to you and ignore, just use nouns and verbs, I'm talking to you as a human. You will not recognize if I'm talking about case 1 or case 2. If you have a simple question, just like rental, advertise property as a business. If you have simple questions, you can ignore everything except nouns and still do a good job. But if you want to understand the difference, if you want to get recommendation about your case, which is either then you have to take into account everything. So this is the point. Let me talk about this example. So keyword-based analysis doesn't help. Phrase-based analysis for this case also not good enough. Enough resolution helpful, but still not enough. Let me show the example. We need to rating for yourself and deducting from total income rating to someone. So the second case about adding subtracting income is linked by means of the rhetoric relation of elaboration. Elaboration is more detailed. So if you have two parts of text and one is saying the same in more detail, you have to index it specifically. You cannot just combine and grant, right? You have two portions of text. One is introductory, and the second is more specific. If you know that, your index, you build your index much, your structure is going to be much more accurate, right? So these kind of questions, by the way, on Google, on search engine don't work very well, because for that you really need to not just a phrase level combination, but you need how phrases are connected in terms of rhetoric structures. Yes.
How does a negation play in all of this? If I said a sentence, I want a jacket without buttons. Without is a preposition, but it's going to be dropped.
Okay, so if I want something without something, then you cannot match these trees, because basically you violate the continuity. So in my example, remember this pump. It's a pump with something and pump without something. If you just search for pump, it will still match. But if you search for the whole expression, it will not go through node, because the subgraph will be interrupted. So going to be two independent parts, which are just single words, right?
Yeah, well, I could
So
have
this
said-
mechanism.
If like doing product search, one
Yeah.
could say we have jackets with zippers, and the question is jackets without buttons. Those should match.
Okay. With something and without something, see, these keywords, these parameters are irrelevant. We don't have ontologies that having something excludes something. We don't know that. We only have language phrases. So if we have something with something and something without something, we only match the entity but not the attributes, right? So using keywords, we match attributes, but that's not a relevant thing in your example, right? Okay. So just briefly, evaluation here, product recommendation, travel, and Facebook, which I mentioned. The way it works, I took Big and Yahoo as a baseline. For this domain, I take shorter sentences without Parse Thicket than 2, 3, 4, and then observe using Bing and Yahoo API how it can be improved. And it's a manual. So for complicated questions, we have average about 60% precision. We don't talk about recall here. We don't know what is available. We select from the available set. So sentence gives, in this case, 11. Then additional information about rhetoric structures, additional 6. And again, this is for complicated queries. The more complex the sentence, the higher contribution of this approach. Yes.
If you have a paragraph matching to a longer document,
Okay.
and you do these thickets, do you ever do anything like an edit distance, like how you could transform the document to see if it closer matches?
Okay.
I mean, I don't
So-
know, that'd be like operations on the graph or the figure.
So ideally, and we don't have this model yet, we have a model of the level of paragraphs, but paragraphs also don't occur randomly. They occur in a sequence, some sequence, although that's a more complicated discourse. So in this approach, for longer sentence, basically too complicated. For longer document, for shorter document, you extract each paragraph and then you match each with each. And think of edit distance as like edit graph distance now, not keywords distance.
That's what I meant, yeah.
Yeah. Full ontology approach is complementary. And there are paper published on this topic. We do this approach. We build ontology automatically by web mining, and then we combine. So let me just give you a definition how ontology works. Ontology is a tree, so that if we have keywords in a query, you map it into this tree. then you have a set of candidate answers, and these answers should have these keywords. So the higher the subset, intersection of the phrase for answer with the tree, the higher the relevance. So you use ontology tree to measure the similarity in a complementary way to this approach.
So it looks like a lot of this stuff depends on a parse parser, is that correct?
Yes. So these days they're like Stanford NLP and OpenLP relatively reliable. So if there are error in parsing, they go to problems. But for like still compared to what you lose, if you not use parse information, still they give you a lot.
Does it support very many other languages, the Stanford NLP?
Okay, so Stanford NLP has model for different languages. Really reliable, so I mostly did it for English, a little bit for Russian, a little bit for Spanish. So for Russian it's much harder. The quality of parsing really is a problem. I would say not really good enough to do this kind of technology. And for English, corpus and model is pretty good enough. So even if there are errors, it's not frequent, so you can still reasonably match. The rhetoric structure parsers, they are not available, so we have our own. There are publications on them, but people don't share them. There's no open source rhetoric structure parsers. And those which exist, they are not well suited for search. And for this purpose, we basically built pragmatic rhetoric structure parser. We took the vocabulary, we extract the template specifically for search, because general purpose is really complicated and unreliable. Okay. So basically I'm done. Just to conclude, contribution is to OpenNLP, but the code uses JGraphT for graph stuff, and Stanford NLP also can get input and do parsing by either. And the idea that linguists now can take advantage of graph algorithms, and for graph people, they need a huge corpus of interesting graphs.
You mentioned parse tree normalization earlier. Can you say something more about that?
Okay, so you need to normalize noun phrases. For example, remove preposition. Digital camera with zoom, you convert it to zoom digital camera. You convert, as we mentioned, passive voice into active voice.
And how are you doing that in your?
Oh, for that, there are papers, and we implemented. It's a rule based.
So you implemented your
Yeah, it's a rule based.
on top of the parts.
Yeah, and it's inside this. So basically, if you use this open source, it's already inside it.
It's open source. Do you know of other people using your open source?
Okay, so there are PhD students. I know there are some downloads. Go to this. So this is not many. You search relevance parse trees. So there are basically, you can download Java project, you can download jar, and then there are some papers. We described in detail. This is a taxonomy paper, how you combine this approach and taxonomy, how you automatically learn taxonomy on the web and then combine and improve search relevance. So there are training set, evaluation set. Here, papers and the jar to combine. So OpenNLP is a popular thing, and this is a part of it. So some people get OpenNLP and this from Apache website, but this is my own repository. So this is to run this thing. You also need to install OpenNLP separately.
Percentage-wise, where's most processing time going? Is it the parsing, post-parsing, or graph matching?
Okay, it's parsing and graph matching. So it's about comparable. Parsing and graph matching is comparable. The rhetoric parsing is simple. We have our simple template, so it's not really deterministic. So So parsing is slow, and graph matching, which is phrase matching.
But they're comparably slow, like within an order of
Yeah.
magnitude? Okay.
So overall, it's significantly slower than compared to like access to Lucene search. It's much slower, 100 times slower. Okay, so we have to accept that. So maybe I finish. So to combine that with Solr, you get maybe 1,000 results. Then you get 100 best results from Solr, and you rank limited number. That way, you make it overall plausible.